Good afternoon, good evening, everyone, and distinguished guests, ladies and gentlemen. Very welcome to this PyData Meetup here at American University of Armenia. My name is Reza Malekian. I'm the new Dean of College of Science and Engineering, and I'm so happy to see all of you here. And you could join us for this talk on NLP. So we are also pleased to have our speakers, Arsine Sarikyan and also Levon Chukhajyan from Mindwise Information Technology LLC, and they will talk about NLP for product categorization and attribute extraction from text data. Actually, this is also first time for myself attending PyData Yerevan Meetup, and same as you, I'm also excited and curious to learn more about real-world NLP pipeline. Before I welcome our speakers, I want to mention that there will be 45 minutes talk and presentation on this topic, and after the talk you will have the opportunity to ask your question. Now, I want to ask all of you, please join me to welcome our speakers, Arsine and Levon. Please.
Hi all, my name is Arsine. I am very happy to be here today with Levon and share with you our experience. A bit about ourselves. Levon is data scientist. Our company has already completed several successful projects. I'm principal data scientist with more than 6 years of experience in data science and also a adjunct lecturer at AUA. During my career, when I just started doing data science, most of the time I spent on coding and debugging issues like spending time in Stack Overflow or GitHub issues. But nowadays, everything is changing and you can get almost any answer to your question by ChatGPT. And that's why comparatively simple things became left in a second plan. Like things like data exploration or result validation sometimes left out in a second plan. And even over the time, the prompting requirements became less and less stricter. When, I guess you remember, in the beginning of ChatGPT, in order to get accurate answer, you need to have more crafted prompts, like act as a data scientist. But now you can just have screenshot of your code, copy paste the error, and most of the cases you will get the answer. However, with all of these advances, sometimes there is a gap when you apply NLP in real world. And as data scientists, we need to have this critical and analytical thinking into designing working solutions. Our talk is about using NLP for product categorization from unstructured data from text reports. Text reports represent a huge reservoir of unstructured information. There later we will see the real-life examples of how it is written, but it's really very chaotic. It includes product description written by humans without any rules or regulation. And simple analytical questions like what is the sale of, for example, rice in a country is difficult to answer. When we will have these standardized categories, it really helps tax agencies in the following ways. So first of all is fraud detection and risk mitigation. By standardizing product name across millions of receipts, invoices, and even import declaration, tax agencies can almost in real time have understanding of what's happening in the economy. They can find anomalous activities or even underreported sectors of the economy. Of course, they can have understanding of economy overall and market insight, understand dynamics, purchasing trends, and overall really market trends. Tracking goods through the supply chain. So this is really important, and in Armenia we mostly have these 3 channels. We have imports, we have invoices, which is B2B, and we have final sale to the customer. the same product can be written in different way across all of these 3 channels. But when we have the same category across all of the channels, we can clearly see the flow, the movement of the product. We will have understanding about price margins, volume, and network transactions. And last but not least is policy evaluation and economic insights. Not only they will have a good tool for measuring impact of the policy, but also use that information for designing the better ones. So to sum up, NLP will help to bridge the gap between this chaotic collection of strings and transform it into meaningful information for actionable decision making. Now let's actually see what I mean by unstructured text. So this is real life example of product description from text receipts. Let's have a look at the first column. So if you can't read in Armenia, it's just collection of products. Like we have butter, broccoli, some diesel, and so on. And you can clearly see, first of all, the mix of languages. We have Armenian, Russian, English. Sometimes we have Armenian words written in English, Russian words written in Armenian. So this is really, really messy. But at first sight, you might think, okay, like this is noisy, we get it. But maybe you can do even zero-shot classification or supervised learning for categorization. Bad things first, we do not have any label data set, so we're only limited to unsupervised tools. But now have a look at the second and third columns. These examples were generated by extracting keywords of coconut and green. And you can clearly see how with one keyword you can have different products. For coconut, we can have cream, fruit, shampoo, sweet, juices, everything possible. And the same with the green. So how to handle this? We started, of course, with the extensive research to see what are others doing. Are there some best practices and how to solve the solution? And as I mentioned, we were left with the unsupervised tools. So we started to do clustering, topic modeling, keyword extraction. Then we transferred to more classical NLP things like dependency parsing, root word extraction, main subject extraction, and so on and so on. Unfortunately, nothing of this seemed to work accurate enough. That's why we decided to change the perspective. We started to work more closely with text agents and understand their needs. First of all, we limit the scope of the research. We started to include only goods from supermarkets and electronics, which actually represent this highest volume of transaction in the market, and started to design categories based on the main consumer basket. So we come up around 300 categories, but they have an equal hierarchy. Like we have very narrow categories like rice, fresh chicken meat, all main types of fruits and vegetables, and we have broader categories like we have design things, garden supplies, exotic fruits, and so on. But this was all driven by the needs of the main client. So what's the situation? Now we have raw input data and we have ideal categories. And somehow we need to merge this, right? And we at one moment decided, okay, enough is enough. Let's create label data set. So we came up with this schema for designing NLP. How we created label data set? We browsed the internet and collected the product description information with already available labels. It ensured us that we have high quality reference data, first of all, and second, we manually changed their labels to our categories. I understand that at this moment it can be a bit demotivating because of manual work, but in real world, in order to have results, sometimes you need to make your hands dirty. And after this manual effort, we were able to come up with high quality reference data, around 100,000 unique product names, which were used for doing similarity matching against 10 million unique product names from text receipts. So you can clearly see the difference. This schema enables us to get around 84% average accuracy across 300 categories, which is really good. And fortunately for us, the more important categories have higher average accuracy. The another very important advantage of this approach is that because it is similarity matching, we have this required transparent and interpretability layer, which is critical when you are working with government agencies. Not only they can see why the following product was categorized as follows, but they also have similarity score. And our evaluation showed that the higher the matching score, higher is the probability that category is correct. So now let me pass floor to Levon, and he will walk you more in detail with the technical implementation.
Hi everyone, nice meeting you all. So to proceed with technical overview, let's divide our pipeline into 4 core modules which we'll be using along the way. The first one is data cleansing module. Then we proceed with product categorization, brand extraction, and unit extraction. So to start with the data cleansing module. So the reason behind cleansing and translation is, as Arsine showed, the data can be very messy. It can be in multiple languages. There may be typos, slang used, and vendor-specific formatting. Every vendor can fill the brand name as he wants. For the obvious example is the brand Coca-Cola. The brand can be filled via hyphen or together, or everything can be messed up. And the structure of the input text is also inconsistent. So in some places, the brand or the model or the category can be written in random order. So we need to handle that as well. And also the key problem was to maintain the brand preservation and brand integrity as well. So let's say the brand Coca-Cola is written in Armenian. So we should in the end normalize it to one single Coca-Cola brand. We will cover that in the brand extraction module as well, but to get the idea that we rather transliterate the brand name rather than to translate it completely. And by transliteration, we mean that we treat every letter separately rather than translating the whole word as a one. So this is the flow, how the data cleansing proceeds. So we do the initial cleanup. At first, there are very simple steps that we clean the white space. We fix the cases of the words. We get rid of redundant punctuation marks or ignore the misspellings. And the most important part is that we try to clear the redundant information from the input. So one example is, let's say, as an input, we got a product, certain type of pipe, and there's a lot of information regarding the modifications of the pipe, its diameter, its length, etc. So at this point, we would rather clear that and get rid of that information in order to increase the accuracy of the model in the future extractors and attribute extractors to gain accuracy. So then we proceed to applying custom translation. We need to translate all of the information into English, and the reasonable question will be, why do you need custom translation? So we'll skip the phases 2 and 3 and go directly into 4th step, which is word-by-word translation. We use several external services such as Deep Translator and Google Translator APIs to translate the words. And the next reasonable question will be, why do you translate the information word by word rather than feeding all of the product information at once and getting it back? And as a reasoning, you might say that you would lose some context by translating word by word rather than translating completely. There were two main reasons doing that. The first one is, of course, monetary one, because translating takes a certain amount of money to do, and translating several millions of rows on a daily basis will take a lot of money, and also it takes a lot of time, as this is the most lengthy process in the whole pipeline. So what we do is we do compound token splitting. We split the sentences into words and try translating only the necessary words and fitting them into our dictionary and then reusing them. Let's come back to the custom translations. The reason was that for several Armenian and Russian words, the translations were completely messed up and hurting the accuracy by a huge margin. So we decided that we need some short list of custom translations that will increase the accuracy of further key attribute extraction. To the brand handling. So we discussed how we should preserve the brand integrity, not to translate it, but rather than to transliterate it. We'll cover it later, but at this point, it's important to understand that we don't need to translate it. Rather, we should swap it with a placeholder, ignore it for now, and then we'll get the normalized brand back into the product description. And in the end, we do the final normalization, which is very similar to initial cleanup, just to tidy things up at the end and get everything ready for further use. So to cover up, so we are handling the brand transliteration by replacing them at this point. We do word level translation, and also we do abbreviation handling, meaning that for certain abbreviations, we would rather expand them and use them so the model will understand better the context of the product for which it's trying to extract the attributes. So for the people without any NLP background, we'll try to understand in a couple of minutes how the models understand text. So first step in the NLP is the tokenization part. So the token is the smallest unit that NLP models work with. It can be a word, it can be a phrase, it can be a part of the word. For example, the word unhappy, which doesn't fit this context at all, will be split into un and happy. So it will consist of two tokens. Another example is, of course, PyData. PyData will be split in Py and data. So and this the tokenization process happens via tokenizer. The tokenizers are, let's say, smart tools which are able to divide these sentences into tokens. They have extensive vocabularies and they know exactly which token corresponds to approximately which vector, and we will cover vectors later, but basically there are two steps. Either the vector is present for certain token, and if the vector is not present for certain token, it has a smart splitting mechanism which will try to understand how to map this vector according to the tokenization rules. So how we turned those texts into vectors. This is a simple two-dimensional vector. Of course, in real life, those vectors are, in our case, 768 dimensional vectors. It depends on the embedding models, on the tokenizer models, but for the sake of simplicity, we will go through this. So every token is mapped as a vector, and you can compare those vectors by measuring angle between those vectors. And the smaller the angle, the closer those words or vectors are in their meaning. And the term for that is cosine similarity. So we will treat the output of cosine similarity as a score, and that's the higher the score, the closer the words are in their meaning. Yeah, and in the end, if you tokenize certain sentence, you get as an output number of tokens. Those tokens are converted into vectors, and if you want to understand the meaning of the whole sentence, you sum up the vectors. So there are multiple ways to do that, but in general, that is not relevant to this topic. The important things are the transformers. So you would ask, what if I tokenize same sentence, but the places of the words are switched, let's say. So the answer is the transformers. The transformers are core tool that is used in GPT, in BERT, or other technologies. And the thing is, they understand the context of the words that are being embedded. So in the example, we have two sentences. The first one is Apple is tasty, and Apple just launched a phone. Transformers are self-attentive models, so they know for each word by which words it's being surrounded. And if the context is that the word tasty is some adjective to the apple and defines, let's say, and hints us that it's a fruit, so in this context, apple is a fruit. In other way, it represents the company. Okay, then how we use those in our product categorization model. So first thing we did, we gathered the reference data Arsine talked about. It's about 100,000 rows. It's a huge table, but we will cover main three columns that will be used. Sure.
Words have different lengths, and all in which space we can
sure.
this,
Sure, we will address that question if possible by the end. But the short answer is that everything is being normalized, so the length of the words or length of the sentence does not matter. You can compare a single word to the single sentence. But we can talk about that in detail in the end. So regarding the reference data, let's focus on three main columns that were used. The first one is product name, the second one is the category of the product, and the price of the product. It's curated list, so we trust that reference data, and we will be matching the input data with the reference data by the end of this model. And what we do after gathering that reference data, we embed each and every product name and each unique category. So we have those embedded vectors, so we can compare the input data which we will embed using the same model to it and find out whether those are close in the meaning or not. And also we store it in fast vector index in couple of words. It's a way of helping us to find the correct vector at a much higher pace. That means rather than trying to find the highest scoring vector among 100,000 rows, you rather cluster those rows into clusters and then find the vector you're looking for at a much higher pace. So basically it's very similar to k-means. Then we already know the overall process. So to sum up, we clean the data, we translate the data, we embed the data, we already have the embedded reference data, and we need to match those two together and find the highest scoring reference data samples. So the matching happens in two ways. The first one is lexical matching. So basically we should forget everything we just talked about, the embeddings, the vectors. This is the most easy and popular technique to compare words, but it's fairly similar and fairly not sophisticated. So it just compares actual words. It ignores minor differences in punctuation, in spelling issues, or in the order of words. So the example is that apple juice bottle and bottle of apple juice. So we have the conjunction of, so we can remove that conjunction, reorder the places, and those words are those sentences are fairly similar to each other. So this, if we do lexical matching between those two sentences, it will result in a fairly high score. However, the limitation of lexical matching is that it doesn't understand any context and meaning of the words. So apple and fruit, are all, even though they are related words, they will not result in any similarity. So for that, we use semantic matching. So semantic matching, we remember what we talked about regarding the embeddings and vectors. So it uses the embeddings to prepare the vectors, compare the vectors. If the cosine similarity and the angle we discussed is fairly small, then it results in high similarity score between those inputs. So an example again with apple juice bottle, but now we have bottle of fruit juice. So it's not bottle of apple juice, and even though the words are different, we'll get high similarity score. Same example for, let's say, face lotion and moisturizing cream. They are completely different, but they have high similarity score. The reasonable question to ask is, if you have such sophisticated tool as semantic matching, why would you even consider using lexical matching? The answer is that in certain scenarios, you better sacrifice the semantic matching's like complex attitude to the problem to trying, let's say, go the easy way. So we apply lexical matching in, let's start with, we have isolated and regular matching. What does that mean? If we are in some sense confident that we will be matching the product within the right category of the product. Let's say we're trying to match cherry, and we for a fact know that we're matching it for with certain amount of other cherries, then we will use lexical matching. So let me bring you an example so it makes sense. So imagine the input is a washing machine from LG, and the model name is, let's say, WM101. So the input is LG WM101. So maybe LG produces refrigerators which are written as LG RS101. So semantic matching will produce a pretty high score in those, but lexical matching, as it compares just the words, it will result in a lower score. So basically, by using semantic matching, we avoid getting a lot of false positives for in certain cases. Also, we do isolated matching by filtering products by certain criteria that we get from the SRC. So let's say there are certain types of products that have certain codes, so we have certain amount of confidence that those codes are written correctly, though it's not always the case. But we can discuss that later. So we basically already discussed this. We use lexical matching in isolated matchings. When we try to rather do word-by-word comparison rather than the examples I brought, let's say comparing face lotion with moisturizer. And the same for the semantic matching. We use face for fast lookup, and we use cosine similarity to measure the similarity between those two. We have certain thresholds for both semantic and lexical matchings. If we exceed those thresholds, then we consider that we have certain amount of confidence that the extraction of category was correct. Now to the price bin filtering. So let's start from the back, from the example. The example is, we imagine that the input data is iPhone 16 Pro Max, which of course is a pricey product. And it so happens that the highest similarity match we get from the reference data is iPhone 16 Pro Max case, which not only completely different price segment, but also completely different type of product. One is a smartphone, one is a phone accessory. So what we do, we try to do price binning. We fix, as we have both price of the product in the reference data and input data, as the product being inputted into pipeline, we try to filter out the reference data for that price bin and try to match the product only through that product's in the corresponding price bin. And it will help us avoid such cases as in the example. Another way of picking the best selection, we saw the example that the iPhone might be matched with the iPhone case. Another example is that maybe assumption is that maybe top scoring category is not always the correct one. And it might be deceiving only to trust the highest scoring category, as maybe the second scoring candidate has almost similar score, off by, let's say, point, and after that 3 digits. So what we do, we try to select top 5 candidates from the reference data we just found, and then pick the correct one from those 5. The one method would be, and the most obvious one would be the majority voting. Let's say if 2 candidates have category apple and 3 candidates have category banana, you would pick the banana as 3 is larger than 2. However, what if the top 2 scoring candidates are apple and 3, 4, 5 are banana? So you can't completely trust the majority voting. So what you do, first you try to calculate relative weights of each candidate. So you divide the weight of the candidate by the highest scoring candidate. Then you try normalizing weights by dividing the weight to the sum of weights. So we do this, so sum of normalized weights is always 1. And then we compute the final score for each category by multiplying each candidate's score by each normalized weight and summing that up. The next question.
But there exists an infinite number of weighted average of the corresponding.
Sure, but please let's address that question in the end, if possible. Thanks. Yeah. So also, what if the price binning we just talked about does not work? And again, even though we performed price binning and we performed picking the right category from top 5 candidates, is not good enough. What if, let's say, the price bin corresponds to 2 reference products? So let's say we have a washing machine of a price 150,000 drams, and in the reference data we have 2 best matches. The one is 160,000 drams and other one is 900,000 drams. And consider the price bin to be from 100,000 drams to 1 million drams. So even though they're in the same price bin, it wouldn't be reasonable to adjust the score based on how close the price of the candidate is to the input price. So fairly easy formula to consider is this one. So we try to slowly decrease the score. So price factor will be a number between 0 and 1. And as the price diverges from the input price, the price factor will become a lower number. Thus, it will decrease the overall score of the semantic similarity we calculated. So the R in this formula is relative price difference between the candidate and the input prices, and the M is the coefficient for price binning. We use this coefficient because, let's say, for the category of apples, the difference between the price of apples can be 3,000%. You can either buy an apple for 200 drams or 5,000 drams, but that can't happen, let's say, for the iPhones. So their price is fairly similar in percentage-wise. So then we adjust the score based on the price factor, and again we calculate the final score for each category. Then we proceed to brand extraction model. So we have 2 general approaches of brand extraction. The first one is brand extraction via extraction and brand extraction via matching. So what's the difference? The first one is we again do compound token splitting. We try to break down the input product data into words or groups of words, as brands may be a combination of words. And then we try to evaluate and score for each probable brand candidate. So each candidate gets penalized or boosted based on certain criteria. It can be boosted for reasons like it's enclosed in quotes or brackets, or it starts with a capital letter, or it can be penalized if it's a common English word, or it's get penalized if it's common color, and it's get boosted for certain criteria if it's found in reference data, or if in the input data it's being found, the candidate is being found in other input products as well. So the brand Apple, even though it's a common noun, it will be penalized, but as word Apple appears in the reference data and as it appears very frequently, it will get a boost that will overrule the penalty caused by it being a noun. Also, the transliteration part we discussed. So basically every brand is being transliterated as the people's names do. And to the scoring part, how confident are you that you extracted or matched the brand accurately? For brand matching, what you do is you match the candidate rightly with the reference data's unique brands using fuzzy matching. And the resulted score, that how those two are similar to each other, is a certain number between 0 and 1, and the higher it is, the closer they are. Fuzzy matching also is used in the normalization. So the Coca-Cola case we discussed, it's written with a hyphen or written with a space, so it covers it all. Regarding the brand extraction, rather than matching the candidate with the reference data using fuzzy matching, you first try to score, to extract the score of the candidate based on, again, multiple criteria, such as we discussed, whether it's enclosed in quotes or is a common noun, or the global frequency we measure. So in the end, we extract several candidates with different scores. The scores vary from 0 to 100. We pick the highest scoring candidate, and then, only then, we match it with the reference data we have. Okay, and after that, as we already have the category and the brand of the product, we need to cross-check whether those two match each other or not. So if there's a chocolate bar, probably if you extracted word Apple, then it's incorrect, as Apple does not produce any chocolate bars. So what we do, we cross-check it. We have, again, a curated list of category and brand pairs. We go and cross-check it. If that's the case, then probably we got something wrong. Wrong is either in category or in brand. We then evaluate which one is more likely to be accurate, and then try to trace it back and pick the correct brand and category based on the more confident attribute we extracted. Yeah, and in the end, both of those matching and extraction mechanism, we pick the one with the highest score, and if the result does not exceed the threshold, we assign it to be a known brand or not extracted at all. And in the end, the unit extraction model. So this is fairly simplest one, even though it contains a huge amount of work. So first thing we do is pre-processing and normalization. We already had this part in the data cleansing model. However, the difference is that compared to brand and category, they're not necessarily, the unit is not necessarily filled in the product description. the data we get from CRC can contain the unit in several other columns as well. So we need to cross-check and understand. First, we need to understand where the unit is placed, and the second case is that there may be multiple units. Let's get back to the example of the pipe. Let's say they're selling a pipe, one piece of pipe, and that pipe has 1 meter of length and 110 centimeters of diameter. So which one is the correct unit measurement that we need to extract, and which one do we need? So we gather them all, and we have a tier list. We try to evaluate which one is the most relevant unit measurement for each one, and we proceed with the one for which we have the most confidence that it will be the most suitable for the further use. Then we do dictionary-based mapping. We have, let's say, multiple ways to write down kilogram. It can be kilogram, it can be kilo, it can be kg. So we map everything back to the single standardized unit. Then we do pattern-based extraction. This is again the part where we understand whether it's the unit we're trying to extract or it's some irrelevant unit that will be, it's just a characteristic of a product. Then we do unit conversion and standardization. We bring everything to the single unit. We bring kilograms to grams, liters to milliliters, etc. And we adjust the numbers, of course, as well. And then, based on the output, we also provide a score on how confident we are on the unit extracted. And if we're not confident enough, or there's some missing information, then we consider that one piece of that product is the most appropriate unit to be assigned. Here are a couple of examples of conversion. So in the row input, you can see how those 500 milliliters are written down and how they're converted to standardized output. In the second row, you can see that we not only convert those, we also understand whether you're selling a box filled with bottle of juices or you're selling a single juice. And if you're selling a single bottle of milk with no specified size and unit measurement, then we consider that one piece of that bottle is the appropriate fallback assumption. So that's it, and we'll be happy to answer your questions. I guess you have a lot.
Hi, thank you for the great presentation. I actually have two questions. The first one is LLMs have been shown to be quite good at fuzzy matching. So I was wondering, have you tried matching the product names directly to the hierarchical categories you created? So, and for the second question, I remember there was mention on interpretability layer. So I was wondering, is it just the similarity scores, or there have been like different tools used to actually explain the decision-making process of the model?
Yeah, I will answer. Thank you for the question. So matching is done like this, except technical part. We have the second part for adding new products. So you match product to products, and then you match product to categories. This will help to have correct category for newly added product and have this generalizability. But to be honest, based on the data, we have seen that almost in all of the cases, for now, product to product matching wins. And regarding interpretability, no specific tools at this moment is used. So we just said that the product from text categories are categorized into these groups because it is similar to this product in the reference data. Mm-hmm.
Thank you.
Thanks.
Thank you for the presentation. I wanted to ask, you mentioned that you are using fuzzy matching for understanding whether a brand name, which is written like, let's say, with a dash or a space, is actually the same brand. So I actually wanted to understand how did you decide on the threshold, let's say 0.9, after which you are sure that the brand name is like the same, because like in Levenstein distance, you like give it 2 strings, and you receive an output of a floating number. So how did you achieve it in this case?
Yes, so we got extensive amount of label data. So we tried to going back from the label data we have to picking the correct threshold. So if that answers your question.
It was basically a combination of a lot of error and experiments to decide the threshold. Also, at this moment, it's difficult to come up with the examples, but in the brand list, you can see very similar brands overall together, like especially the more coming Russian product name, they have Alyonka, I don't know, some brand of vodka, Alyushka or something like that. So if we lower the threshold, we will come up with a lot of false positive. But for us, it was important to have even small number, but with high accuracy. That's why we set up threshold a bit higher.
It is also interesting. Did you have like different thresholds for different categories of products?
No, we have the same for overall. But that's actually a good idea. Maybe we can try and see if the results improve.
Thank you for the very interesting talk. Which model did you use to compute embeddings, and why did you choose that model?
So we used all MPNet model. It just performed better than the rest. We have very large list of other models used, multilingual, paraphrased model, anything. We even tried these recent BERT-based models with sparse embeddings, but at this moment, the OLMPNet just wins based on our data.